Hey everybody, how's it going today? Today we'll continue our investigation of gases and gas laws by looking at some multivariable problems and the ideal gas law. Let's get started. Today we'll start by looking at the combined gas law, which will apply to a couple of practice problems before moving on to the ideal gas law, which is probably the most useful gas law we'll cover. Finally, we'll apply the ideal gas law to some example problems so you can see it in action. It's worth taking a moment to remind ourselves of what we covered so far before moving on to the combined gas laws. We have already investigated Boyles' law and Charles' law, which describe the relationship between volume and pressure and volume and temperature. Boyles' law is written as P1 times V1 equals P2 times V2, and Charles' law is written as V1 divided by T1 equals V2 divided by T2. If you remember from our discussion of these laws, both of them can only be applied when all other variables are held constant. In the real world, it is often unrealistic to control all the variables except for one. We need to be able to use formulas that can account for multiple changing variables at a time. As it turns out, Boyles' law and Charles' law can be combined without any issues, which leads us to the combined gas law. If we combine both of the first two laws, we get the combined gas law, which is written as P1 times V1 divided by T1 equals P2 times V2 divided by T2. What this means is that the pressure times volume divided by the temperature of a gas at state 1 is equal to the pressure times volume divided by the temperature at state 2, assuming the amount of gas stays the same. Let's look at some examples. So this problem says the volume of a hot air balloon is 30 liters at 40 degrees Celsius and 150 kilopascals of pressure. What volume will the balloon have at STP, where STP is 273 Kelvin and 100 kilopascals? So first things first, we want to write out our formula. We've got P1 times V1 over T1 equals P2 times V2 over T2. We also need to convert this temperature here into Kelvin. So in order to do that, we do 40 plus 273 equals 313 Kelvin. So our T1 is 313. Our P1 is going to be 150, and our V1 is 30. So let's put all of those variables in. We have 150 times 30.0 over 313 equals, our pressure at 2 is 100 times V2, which is what we're trying to solve for, divided by T2, which is 273. So all we got to do, multiply this by 273 over 100, cancel, 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 times 273 over 100. And that whole thing, if we solve that out, is going to leave us with V2 equals about 39.2 liters. Now we need to take the amount of gas into consideration. While this is the easiest variable to control when it comes to gases, it can change, but more importantly, we would like to be able to calculate the amount of gas if given the other variables. This issue is compounded by the fact that all of our problems so far have only worked if we can compare two different states. We have to have a V1 and a V2, a P1 and a P2, and so on. There is a way to get around this, assuming that the gas that we are talking about is an ideal gas. An ideal gas is a gas that obeys all of the different laws under any conditions. We'll talk about which gases are ideal and which aren't later, but for now, let's look at what ideal gases allow us to do. If you've ever filled a balloon, you know that adding more gas to a container increases the volume, assuming the container can expand. This means the amount of gas, which we'll abbreviate with a lowercase n, has the same relationship to volume as temperature does. Remember that as temperature increases, so does volume. This is the case for amount of gas as well, or number of moles, which is where the n comes from. Since number of moles has the same relationship to volume as temperature, we can place n in the same place in our equation as T. This leaves us with a larger version of the combined gas law, which now says that P1 times V1 divided by T1 times N1 equals P2 times V2 divided by T2 times N2. That's a lot of variables to write out, but luckily for us, it turns out that the pressure times volume divided by the temperature times the number of moles for any ideal gas is equal to 8.31. 8.31 is called the ideal gas constant and was determined over a large set of experiments and tests, but it allows us to come to the full version of the ideal gas law. The ideal gas law is PV equals nRT, or the pressure of a gas times the volume of a gas equals the number of moles times the temperature times the ideal gas constant. Let's look at how we can put this formula to use. So for both of these problems, we're going to be using the ideal gas law, which is PV equals nRT. The first one says, how many moles of oxygen are in a 20-liter container with a pressure of 20,000 kilopascals at 300 Kelvin? So first things first, number of moles we're solving for, which is the N. So the N is what we're going to want to solve for. We know that our pressure is 20,000 kilopascals, so 20,000 times our volume, which is 20.0 liters, equals N, which is what we want to solve for, times 8.31, which is the gas constant, R, times our temperature, which is 300. All we got to do is divide both sides by this stuff, 8.31 times 300. That'll cancel. Divided by 8.31 times 300. And we are going to be left with N equals about 160 moles. Second one says, if the gas stays in this container and maintains its temperature, so we know we're going to be keeping the same 20 liters and the same 300 Kelvin, what will the new pressure be if an additional 80 moles are added to the container? So now we know that N equals 160 plus 80, which is 240 moles. Our volume is still 20 liters. Our temperature is still 300 Kelvin. And we are attempting to solve for pressure, P. So, starting with our equation again, we've got P, which is what we're going to try to solve for, times 20 equals N, which is now 240, times R, which is 8.31, times T, which is 300. All we got to do is divide both sides by 20. And when we solve all of that out, we will get P equals about 29,900. So 29,900. And that'll be in kilopascals. Now, if you'll remember from earlier, I said that the ideal gas law only works with ideal gases. I told you I would explain which gases are ideal and which ones aren't later. As it turns out, there is no such thing as an ideal gas. All gases are in some way not ideal. For most gases, this is due to their behavior being inconsistent at extreme temperatures and pressures, or undergoing phase changes to a liquid or a solid. In some cases, a gas is not ideal because of a slight attractive or repulsive force between its molecules. In any case, no gas is perfectly ideal, but almost all of them are so close to ideal that the difference is negligible. If you were working on some kind of nuclear reactor that needed to be precise down to the microliter, it might be worth knowing the differences between an ideal and a non-ideal gas. But for our purposes, we're just going to assume that all gases are ideal and deal with a little bit of difference. Let's review. The combined gas law, which is written as P1 times V1 divided by T1 equals P2 times V2 divided by T2, allows us to do calculations involving multiple changing variables. Adding the amount of gas in the equation leads us to the ideal gas law, which is PV equals nRT. R is the ideal gas constant and is equal to 8.31. Technically, there is no such thing as an ideal gas, but the vast majority of gases are close enough to ideal at normal temperatures and pressures that we treat them as ideal gases anyway. That's it for today's video. Thanks for watching, and I'll see you next time.